Hi everyone, we're Zhengyi and Lu Jie. Our project is Safe Multi-Agent Control under Modal Uncertainties by learning robust control bearer functions. Multi-agent reach avoid tasks are prevalent in many real-world applications, such as drone delivery and self-driving. However, the current safe reinforcement learning methods can't provide the safety guarantees. Even though they minimize the cost, they can't guarantee that those safety constraints are satisfied in training or testing. The safety certificates, such as control bearer functions, can provide formal guarantees, but hard to synthesize by hand. The problem is even more challenging under modal uncertainties and disturbances. In this project, we learn the multi-agent control bearer functions and jointly synthesize the safe multi-agent controllers that can deal with the modal uncertainties. Here's the outline of our presentation. The first part is about the controller synthesis, including learning the control bearer functions and achieve the goal reaching by the reference controller. The second part is the two methods that deal with modal uncertainties. The first one is adding the worst case CBF margin, and the second is injecting noise directly into the dynamics in training. And then we present our experiments and results. We learned the decentralized multi-agent CBF with neural networks to ensure the states of all agents stay in the safe invariant set, and we jointly learned the safe multi-agent controller. In order for all the agents to reach their goals, we generate the reference control input using the nominal controller. And to encode each agent's observation that contains a changing number of neighboring agents, we propose a quantity permutation invariant observation encoder, which encodes the dynamic observation into a fixed length feature vector. The input to the observation encoder is an observation matrix with changing number of dimensions. And the output is a fixed length feature vector. And the output of the whole structure is the control input for agent I.
The major approach we took is adding a worst-case margin to the control bearer function condition and jointly learn the robust CBF together with the safe controller at the same time. The left side of this inequality is the original control bearer function condition to ensure that the controlled agents stay inside the safety set, while on the right-hand side, gamma takes care of the worst-case disturbances by taking the supremum over the DIs. We formulate the CBF conditions into the loss function L, and by minimizing this loss function, we enforce that the corresponding control bearer function conditions are satisfied under the most adversarial uncertainties within the safe set and in the dangerous sets, respectively. We ran some experiments to verify our CBF and safe controller synthesis by controlling 32 agents with the double integrator dynamics. The left plot shows the process when the agents are executing their reach avoid task, and the right plot is visualizing after all the agents have reached their goals. We're using the collision reduction coefficients as the evaluation criteria compared with the baseline LQR controller without safety considerations. We also compare our worst-case margin approach with the one that directly injects Gaussian white noise into the dynamics during the training process. The simulation results show that adding the worst-case margin is more effective than naively adding the noise during the training process. The following bar chart demonstrates the collision reduction coefficients for varying amount of noise during the testing process. The very first blue bar shows the improvement of the nominal model without considering disturbances at all. The following three bars with orange, green, and pink color demonstrates the collision reduction coefficients for the model trained with the noisy dynamics of different noise scales. This approach has really high variance and can sometimes be even worse than the baseline LQR controller. The last three bars show the collision reduction coefficients for the model learned with the worst case margin. This approach is constantly outperforming other models with different noise scales. In conclusion, our approach can jointly learn the robust control barrier function and the safe controller with the neural networks. Using the decentralized framework, we can scale the control strategy to hundreds of agents, even in face of disturbances and model uncertainties.